Okay. So the ideal gas law, and basically what that name comes from is, in fact, all the gas laws are sort of imagining gases. It basically means this gas law works for these sort of perfectly imagined gases, and it turns out it works for most gases most of the time. I don't know. Don't worry about the name too much and what it means. But here's the formula. PV equals nRT. We often call that PivNert. Now, this ties together the other variables we're used to, P, pressure, volume, and temperature, but it also throws moles in there, like we've just been talking about with moles, and then R. So let me just write down what each one of these things is. The other, and also it needs special units. I should say specific units, maybe not particularly special. Which the other gas laws did not necessarily, except for Kelvin. So P is going to be pressure, of course, but it must be in ATM. N is moles. R is a constant. So if you're not familiar with constants in mathematical equations, it's just like a magic number that makes this thing work, okay? So R, you never have to be told R. It doesn't have to be given to you on the problem, and you're going to get this number. It's one of the things you get on the back of this periodic table, and it is 0.08. I usually just say 821. It's got a really weird unit. Liter atmosphere per Kelvin mole. And it has that unit, so things like cancel out. It also tells you all of the required units. And then T, of course, is temperature, which, like all the gas laws, has to be in Kelvin. So again, this formula is given to you on the periodic table. Value of R is given to you on the periodic table. Even the unit for R is given on the periodic table. So that will help remind you that these are the units that you need. You need liters, you need atmospheres, you need Kelvin, you need moles. And if you don't have any of those, you have to convert. So let's look at some examples of this, which is, I believe, 10 says. The equation, no, the equation is on. So yeah, you're getting the combined gas law, the ideal gas law, value for R, all the stuff that it says on the top of that review assignment there. Okay. So if you look at like number 1 on the next page where it says ideal gas law, it says what pressure will be exerted by 0.50 moles of a gas at 25 Celsius if it's contained in a vessel whose volume is 650 milliliters. All right. Is it my page numbers are different. It's 10, the one that says ideal gas law at the top. Okay, so it's asking us to solve for the pressure in atmospheres. So that's fine because that's the unit that it will put out all the required units. In other words, it will output those. So I personally, especially with this equation, I like to do the algebra first with the variables. You don't have to, but I like to do it, kind of get it out of the way. So to get pressure by itself, I'm going to divide both sides by V. So if we rearrange this equation to solve for pressure, we see that pressure equals nRT over V. Now from there, we just need to put stuff in this equation, and we just need to make sure that we have the right units for everything. And if we don't, we're going to have to convert them. So N is moles. It does give moles, so that's fine. So 0.450 moles. And then R, remember that's just, I don't need to be told that. That's a magic number. It makes this work. I can just put that in, 0.0821. I am going to have to convert my temperature, as usual with all these gas laws. What's my number here to convert? 273. There you go. 298 Kelvin. And then another unit that we're going to have to convert. It's given in milliliters. So the milliliter to liter conversion is one you do quite a bit. I think we talked about it a little bit remotely. You're moving the decimal 3 spots. There's 1,000 milliliters in a liter. So it's 0.650. If you can just remember that, liters to milliliters, it's always 3 spots. It's going to be 0.650. Exactly, yeah. If you were going liters to milliliters, you would move 3 spots in the other direction. And so the way that the units work is the units of R all cancel except for it's going to give me a pressure in atmospheres when I solve this. So I think you end up getting about 16.93. If we want to be really good, the least number of sig figs is 2, I think. You could have 2. 650 has 2, so 17 atmospheres. Questions about that? Let's try another one. What volume will 12 grams of oxygen gas occupy at 25 Celsius and a pressure of 0.520 atmospheres? Okay. So it wants to know volume, just like the last one. Or no, not like the last one, but I can solve this by dividing both sides by P. And again, I'm just doing the algebra in advance. You don't have to. But I'm just doing the algebra in advance with the variables and just getting that out of the way, and then we can just plug stuff in. So once we solve that, we need to put stuff in, but we need to make sure that we have the right units. Okay, something that's going to be a problem is we have 12 grams. All right, this ideal gas law does not work with grams. And then it says oxygen gas. Oxygen is O2. It's Brinkelhoff. It's the O in Brinkelhoff. So what I'm saying is we need to do one of those conversions that we've just been doing before we can put the number into the equation here. So find oxygen on the periodic table. Its mass is 16, but I multiply that by 2 because it is a diatomic element. Okay. So, whoops. So what we've just learned is that 1 mole of oxygen has a mass of 32.00 grams. When you need to convert something, start with what you're trying to convert. We make the train track here, the 1 mole on top, put the 32 on the bottom. So that's about 0.375 moles. So just a little mole conversion there like we were just looking at because I need to use moles in this equation. And by the way, guys, you know, be careful about rounding like at too early of a phase, or you're going to start to get answers that are pretty far off. So definitely keep extra sig figs if you need to. Like you wouldn't want to round this to 0.4, for example. Okay, so 0.375, that's my N. R is 0.0821. Temperature, I do need to convert my temperature. It's 25 Celsius, so I would go 298 Kelvin. Add 273 to that. And then divide by the pressure, or sorry, divide by the pressure, which is 0.520. So the hardest part, really, for most people, is just making sure all the units are correct and getting all that figured out. It's going to give us an answer in the same like required unit, which is liters. So that's going to be about 18 liters. Questions about that? Let's see. Let's do 4. A 50 milliliter flask at 25 Celsius contains 0.0200 moles of Cl2. What is the pressure in the flask in kilopascals? Okay, well, it wants pressure again. I can solve for pressure. I can get pressure by itself by dividing both sides by V. Now, fortunately, it does give me moles here. So I don't have to worry about that. I'm going to have to do a couple conversions, though. 50 milliliters. We move the decimal 3 times. Because we can't use liters. So that's, that's that many milliliters. So we got, that's 0.05. I'm going to try to reconnect here. No, because it's already given it. Now, if it gave a mass, then yeah, then we would do that conversion, but it's already given me a moles. Sorry, I gotta try to. Let me see if I can make it project again here by using this. Sorry, folks watching at home, we're having some technical difficulties here. So yeah, no, we do not need to convert the we don't need to convert the moles. So pressure equals, the moles is 0.0200. Whoops. Times R, which is 0.0821. In terms of my temperature, which I do need to convert to Kelvin, which is 298 Kelvin. And then the volume is 0.0500. So if we solve this, like I was saying, it's gonna be, if when you solve all those required units I mentioned, the ideal gas law puts those out. So this is a pressure in atmospheres, but the question asks for kilopascals. So like we've done quite a few times, we need to take advantage of the fact that we know what standard pressure is in both of these things. And so I can convert this pressure. As I've said before, those values are also given to you on the thing. So 101.3 kPa is 1 atmosphere. Basically, we need to multiply by 101.3. And then what that's going to do is that's going to give us the correct unit for this thing. It's about 991. Questions about that? Why don't you guys try number 7? So 7, it does give you a mass in grams of helium. So you are going to have to convert that to moles. Take a second and try number 7. So here I have number 7 worked out. And, you know, like I said, the challenge really for most students is just making sure all the units are right and recognizing that I need to convert this to moles. Helium's not diatomic, it's just regular 4 grams. So that's 1.31 moles of helium. We put that there, put in R, put in the volume. We should get about 94.8 Kelvin.
I got 95.3.
Are any of these things different that you put in?
I put in 1.3 instead of 1.31.
Yeah, that'll make a little bit of a difference. I try not to round till not too much to the last step, but not too big of a deal. Okay. So here's the next thing I would like you to ponder. If you flip to the next page, number 9 is not a math problem, but I would like you to read number 9 and just kind of ponder it for a second and see what you think if you can come up with an answer to A and B. Okay, so what do we think? We got these 2 containers. They're identical, so they have the same volume, the temperature's the same, the pressure's the same, all that's the same. They have the same number of moles of gas. What do you guys think? They do. So if we think about this mathematically, if the pressure is the same, if the volume is the same, if R is the same, if T is the same, then N has to be the same, right? So yes, the moles would be the same. What about the mass, though? Would that be the same? It would not. Because every gas, unless there's a big coincidence, is going to have a different molar mass. So that's the thing about moles. Remember, it's always the same number of things. It's always 6.2 times 10 to the 23rd things, but that doesn't mean it's the same mass. A dozen is always 12 things, but that doesn't mean it's always the same mass. A dozen eggs, a dozen bowling balls, very different mass. So the moles is the same in these 2 containers of gas, but the mass is not. So that's kind of an important, conceptual idea about this. Does that make sense? Questions about that? So we look at number 10. 10 is basically a math problem, a quantitative math problem that relies upon the exact same idea that we've just been talking about. So, for instance, it says 2 200-liter tanks, so pretty big tanks, 200 liters. They're both 200 liters. You don't have a 10?
Number one is the same. Community saying, right?
Does it?
Tanks are to be filled separately with
Yeah.
Yeah, that's one for us.
Oh, really? Okay. Well, that's the one I'm referring to. I don't know what's going on with that numbering. So it's 200 liters. They're at pretty high pressure. 135 atmospheres is a lot of pressure. So these are jam filled with gas. And they're 24 Celsius. So what it's saying is one is filled with helium and one is filled with hydrogen. Hydrogen is H from Bringelhoff. It would actually be H2. So it's saying what is the mass of hydrogen and the mass of helium in each tank? Here's how we could solve this. Remember, you can always convert from grams to moles of anything as long as you know what gas you're dealing with. So let's figure out how many moles are in this tank, right? We've already established from the previous problem the moles is going to be the same in both tanks, so we don't have to do that twice. So if we solve for moles, PV equals nRT, divide both sides by RT. So PV divided by RT equals N. Everything is in the right unit already except for the temperature, so that's pretty good. 135 atmospheres times the volume, which is 200 liters. Divided by 0.0821 times the temperature. 24 Celsius is 297 Kelvin. Yeah. What's that?
I think never mind.
Type something in wrong, maybe?
No, I feel like for some reason I thought it was the equation that you added to and then
Add 273. Celsius to Kelvin is add 273.
for some reason I got the 793 mixed up. I'm like, that didn't seem right.
Yeah, that'll get you a wrong answer if you transpose those. So, okay, so that's how many moles are in both tanks. We don't need to do that twice. So what it's saying is, how much does the helium tank weigh, the gas in it, and how much does the hydrogen tank weigh? So we can do one of these mole conversions here. So there's two answers. So for the helium, we could just look right up on the periodic table. 1 mole of He, it's not diatomic or anything. It's basically exactly 4 grams. So now, what goes up must come down. Put the mole on the bottom, put the 4 grams on top. So the helium tank contains 4,428 grams. So you guys know helium is kind of like running out. We're consuming helium at a faster rate than we're using it. Or there's actually kind of more being made because it ends up being made from like radioactive stuff and different things like that. But
So the thing is, more nuclear power plants.
so, well, what I'm saying is, helium is really important for certain things like MRIs and stuff. So, of course, it has to be reserved for that use. And things like, it might be too expensive for things like party balloons. Probably within your lifetime, I bet.
Wait,
So,
no more
party
nuclear
balloons.
really
Yeah, no more getting your voice really high, and possibly no more party balloons.
That's it.
It's a
Cut off
sad,
3 nukes, make more helium.
sad day.
Make a sun. Tons of helium. You know? That's what we gotta do. We gotta make our own sun, make our own helium.
That will solve our energy problems, for sure. So let me just say one thing really quickly before we talk about making your own sun. The only difference in the hydrogen calculation is hydrogen has a different mass, as we were talking about in the previous problem. It's H2, it's 2.02 grams, so it's going to be roughly half the mass. So that's the only difference in that one. Questions about that? Helium is 4, straight from the periodic table. Hydrogen is 1.01, but it's one of those tricky diatomic ones.